I'd like to do an example using Newton's laws, and this is sort of a fun contraption. It highlights a number of subtleties for these problems. Also, it requires some pretty good visualization skills. So I have this sled here in yellow, and it has a pulley on it, and I've got a rope wrapped around a pulley which is attached to a mass that's sitting on the sled. So there's friction between the sled and the block, but there's no friction between the sled and the ground. And so someone is pulling on this rope with some force F. And the question is, what is the maximum force such the block does not slip on the sled? So first of all, let's just stop for a minute and visualize what that means. So I'm pulling this thing, and as long as the friction the frictional force is high enough, the block will stay at rest relative to the sled, no movement here, but then I'll be able to pull this whole system along the ground here because there's no friction on the ground. However, if I pull too fast, give it too large a force, then the block here is going to slip relative to the sled. Okay, so I need to find what that maximum force is. Obviously, there's this coefficient of static friction between the block and the sled, and as I increase this force, this is going to increase to its maximum value, and then any higher force, it's going to slip. Okay, so I sort of have a good visualization of what's happening there, and so now I need to go about and solve that. How am I going to do that? Well, I guess the physics that applies to this problem is Newton's laws again. So I want to choose an object and then find what forces are on that object. So the first object I'm going to look at is the block. I think that sort of makes sense. So first of all, choose an object. This is the block. What are the forces on this object? There's gravity. I'll call F sub g. So there's this string which is attached to it. So we use our string model of tension. There's some sort of tension force on the block. And then there's the contact force between the sled and the block. Okay, and so there's friction involved that's holding it there. So I think I want to break this contact force into a normal force, which I'll call N, and then a friction force, which I'll call F sub F. Okay, so these are the forces on the object. That's the only thing. The only thing in contact with it are the sled and the string or the rope, and then there's gravity. So that's all there is to it. So next up, let's look at free body diagram. So I have my point, and so there's a force due to gravity, which is straight down. And there's the tension force. In what direction does the tension force act? Now this is important. You always have to remember our models of these systems. It's somewhere up here, someone is applying a force to the rope in that direction, but that doesn't determine how the tension force acts on an object. The tension force acts along the direction of the string at the point where the string connects with the object. That's the model of the tension force. We can't ever forget the details of that model. So the tension on the block is in that direction. Okay, so we also have normal force, the normal force from the sled to the block, and that normal force points in the direction from the agent to the object, perpendicular to the surfaces between them, and so that's up. So what direction does the frictional force act? The frictional force is tangent to the surface, fine. It's opposite in the direction the object moves relative to the agent, if there were no friction force present. Okay, what does that mean? So imagine there are no frictional forces here between the object, which is the mass, and the agent, which is the sled. So if there were no friction there, when I pulled on this rope, the block would move to the left. So the block would move to the left relative to the sled, which means the frictional force points to the right. So the frictional force points to the right. Again, there's just no you have to keep going back to the model of these systems and applying the rules of the model to be able to get the right direction of these forces. All right, so now I need a coordinate system. We'll call to the right positive x. We'll call up positive y. And so now I can, everything is along the axes, which is convenient, so I can now sum the forces. So I have this force due to gravity. Well, I can do this up here. Force due to gravity, and it has nothing in the I, nothing along the x-axis. It has the magnitude equal to the mass of the block. Remember, I have to distinguish that from the mass of the sled. Mass of the block times g. It's in the y direction, and it's negative. Okay, so I also have the tension here. So the tension is along the negative x-axis, so it has a magnitude of t. It's along the negative x-axis and nothing along the y. The normal force has nothing along the x and its entirety along the y. And then the force due to friction has its entire magnitude, which is the coefficient of static friction times the normal force, and it's in the positive y direction and nothing, the positive x direction, sorry, and nothing along the y. Okay, so now I can use these, so I want to sum these forces. The vector sum of all these forces, this is on the block, is equal to the mass of the block times the acceleration of the block. And the mass of the block is it's at rest relative to the sled, but the whole object is moving to the right, which is the positive x-axis. So it has some mass of the block, acceleration of the block on the x-axis plus nothing on the y. So remember, again, this is a key part of the visualization. We said that the block is not slipping on the sled, but the whole system is accelerating to the right. That means the block has to have some acceleration to the right, and that's the positive x direction, as we've described. Okay, so you have to have a clear visualization of this problem to be able to get the right context. Okay, so now we can sum the x and y components, and what do we find? We find from the y component that the normal force, the normal force of the sled on the block is equal to the mass of the block times g. That's probably useful to know. And then I have that from the x component, I have negative tension plus the coefficient of static friction times the normal force is equal to the mass of the block times the acceleration of the block. All right, well, I can substitute in here for the normal force, and also I know that the magnitude of the tension is equal to the magnitude of the force that's being implied. See, this is, again, one of those things that just sort of shows up in homework problems and tests and everything. Here's sort of a disembodied force. There's another object on the other end of this rope. It's applying a force to this rope, and that puts a tension force within the rope, T, which is the same everywhere. Okay, so tension then is equal to the original force that were given in the first problem, in the introduction to the problem, that's being applied to the rope. So if I substitute the tension into here, the normal force into here, I get that negative F plus mu sub s, mass of the block, times g is equal to mass of the block acceleration of the block. And I might rearrange this a little bit and show that my force is equal to, if this goes positive, this becomes negative, and this becomes negative. So then when I bring this on the other side, it becomes positive. Force is equal to then mu sub s m sub b g minus m sub b a sub b. All right. So that doesn't, I know that the coefficient of static friction will reach its maximum value right before it slips, but I still don't know what that is because I don't know the acceleration. So I have to find another object on which to do F equals ma. Now I remember when I did 2 blocks before that I could look at as the entire system as one object, as long as its components don't move relative to each other. So the condition that the block does not slip means that the sled and the block don't move relative to each other. So I can look at this entire system as an object. That's one reason why I wanted to do this, to see how powerful that is. And so as long as these objects don't slip relative to each other, I can look at this entire thing as one object. So in this entire object, what are the forces on this object? Well, there's the normal force of the ground on the object, but no frictional force. There's gravity, and then there's the tension. The tension is the only other thing that's crossing this orange line, that's in contact with this whole object. So for the system, my 3 forces are the normal but no friction, gravity, and tension. If I do a free body diagram for that, I have normal, the force due to gravity, and then tension. Again, the tension is where it's sort of in contact with the object, which is it's often going towards the right. So if I call that the positive x direction, up y, then I have that let's sum the forces. So the tension gives me the magnitude of the tension, I plus nothing in the j. The force due to gravity gives me nothing in the I, and the combined form of the force due to gravity is the total mass of the block plus the mass of the sled times j hat, and it's the negative y direction. And the normal force then is 0 I plus its entirety, the entire magnitude, and in the positive j direction. If I add those together, I get the total mass, the sum of the forces on the total system is the mass of the system, the mass of the system, which is the mass of the block plus the mass of the sled, times the acceleration of the system, sys. And that's all entirely in the x direction. So that's mass of the block plus mass of the system, a of the system, I hat, plus 0, j hat. So from this, I get, since the tension is equal to the original force being applied to the rope, I get that the force is equal to mass of the block times the mass of the sled times the acceleration of the system. Now, of course, since the system is just the sled and the block, which are not moving relative to each other, the acceleration of the system is equal to the acceleration of the block. So I'll just call that A. So now I have these two equations. I both solved for F, so I can just set them equal to each other. So I get mass of the block plus mass of the system A is equal to the coefficient of static friction, mass of the block G minus mass of the block times A. And now I want to solve for A. Right. And so I can bring this on the other side, and I get, this is minus, so I get another block term. So I get 2 mass of the block plus mass of the system times A is equal to coefficient of static friction, mass of the block times G. And you see how that works if I add mass of the block times A to each side. This cancels, and I get a second mass of the block term when I factor out the A and combine it with this. So that gives me now my acceleration. My acceleration is equal to the coefficient of static friction, mass of the block, over twice the mass of the block plus the mass of the sled times G. Okay, and so it's not obvious what to check here. We have double the mass of the block because it's related to the frictional force, as well as the total mass of the system. The coefficient of friction is here in the numerator, so if it gets larger, of course, we have larger acceleration. So the sort of things that we can check sort of make sense. This is now the maximum acceleration. This is the maximum acceleration you can use. That will happen before the system can move. The max acceleration the system can have before the block moves relative to the sled. Okay, so we want to find the force, which is easy enough now, because we can substitute that into here. And so the force then is equal to the total mass of the block plus the mass of the sled times the mass of the block, coefficient of static friction, if I bring that out front, twice mass of the block plus mass of the sled G. Okay, so we just substitute A into here, and since this acceleration is the same as the acceleration of the system, and we can find the force. All right, so that's the maximum force. Next, we want to find is what is the force such that the block will not accelerate. So that's an interesting question. What exactly is happening? Let's start by visualizing that here. If I get a new picture, I'm not sure I want to draw a new picture. We'll use this one again. All right. So now I'm pulling the system. Now previously I said the block was not slipping relative to the sled, which meant it and the sled were accelerating to the right. Now I want a force such that the block does not have an acceleration. That means the block starts at rest, or a constant velocity. Let's just say it starts at rest relative to the ground. And then I'm going to apply a force such that it stays at rest relative to the ground. Well, if that happens, what's happening? What's happening then is I'm pulling the sled from underneath it. Remember, the sled has no friction relative to the ground. So once I apply a force, that sled is going to be moving. So if the block stays at rest after I apply the force, that means the block is sliding relative to the sled while the sled is being pulled from underneath it. Huh. Okay. So let's go ahead and solve that. So you can see how it's really kind of important when I ask that question to get a good visualization of what's happening. Okay, so in the first one, I want to look at the block. Let's look at the block. The same forces act on the block as before. There is a tension in that direction, a force due to friction in that direction, kinetic in this case, because it's sliding relative to the sled. There's the normal force, of the sled on the block, and then the force due to gravity. And so now I have everything is on their own axes, so I can look at the x and the y system separately. And so in the x direction, well, in the y direction, I have, if I call that the plus y, I have, well, then again, equal to 0, because it's not accelerating in the y. This is entirely the normal force in the positive y direction. The gravitational force is the mass of the block times gravity, and it's in the negative y direction, so that must equal to 0. So that tells me that the normal force is the mass of the block times g. I had that before. Okay, in the x direction, again, I have the tension plus the force due to friction is equal to 0. I can only do this separately now because I have only my components along the separate coordinate axes. And so the tension is negative the force applied to the rope, because it's magnitude of the force, it's in the negative x direction, plus the force due to friction, which is the coefficient, in this case of kinetic friction, times the normal force. And that's equal to the mass of the object times the acceleration of the object in the x direction, which we said is 0. Remember, if it stays at rest relative to the ground, it has no acceleration. So it continues to stay at rest, so acceleration is 0. So this tells us that the force on the rope is equal to the coefficient of static friction times the normal force, which is given up here. So it says that the force pulling on the block is equal to the coefficient of kinetic friction times the mass of block times the gravitational constant. And we're done. In fact, well, this, I would say, was kind of conceptually more difficult. The solution was really quite simple. The one thing I will say, I did glossed over this a little bit, is are we sure the force of friction was in that direction? So when we pull this, the sled is moving to the right. But that still means that the object, in this case the block, is moving to the left relative to the agent, which is the sled, which is moving to the right. So even though the block is at rest, the sled is moving to the right, which means from the sled's perspective, which is the agent, the block is moving to the left relative to the sled, which means the frictional force then is to the right. So you do have to be a little careful about how those are the direction of the frictional force. In kinetic friction, it's in the direction opposite the object is going relative to the agent that is applying the frictional force. All right, so as a final point to this, there's one sort of interesting object to point to this problem, is let's go ahead and find the acceleration under these conditions. What's the acceleration of the sled? So we have the force such that the object is at rest. What is the acceleration of the sled? We didn't need to do analysis of the sled to find the block, but let's go ahead and do that just for practice. So now let's work on the sled. What are the forces on the sled? So now I'm looking at, I'm going to have to, no hope. I'm going to have to draw this again. So I have the ground. I have a sled. That's why when you work, you always need large amounts of blank scratch paper, because you just need big pictures all the time. Okay, so this comes around here, and this is pulling with some force. All right, so let's look at the sled So the sled is here. This block, everything in yellow. Okay, so what are the forces on the sled? Okay, there's gravity. Fine. We'll call that F sub g. There's the normal force of the ground. There's no friction from the ground, so that's the normal force of the ground on the sled. Now there's a contact force between the block and the sled, and that's a normal and a frictional. So there's this contact force between the block and the sled that leads to a normal force from the block on the sled, as well as a frictional force of the block on the sled. So there's a contact force. And there's also the tension. And this is one reason why I wanted to do this, is that you can see here that there are in fact two ropes passing through the yellow line. That's significant. Each rope is in contact with the object. So there is a tension force associated with each rope that passes through this orange line that comes in contact with the object. So there's a tension force, which I'll call T sub this vector, and the magnitude of that tension force is equal to twice the tension that's in the string, because it crosses through, it comes in contact with our object at two separate points. And so each point it is applying a force equal to the tension on the object. So the total force is twice the tension in the string. Okay, so that's significant. All right, then that's why I wanted to bring that up. Let's go ahead and do a free body diagram. So there's the normal force of the ground on the sled. There's the normal force of the block on the sled, which is pointing down, as well as the force due to gravity. There's a force in to the right, which is equal to, this is the tension force. And then there's the force due to friction. Well, are we sure it's in that direction? So this is now the force due to friction of the block on the sled. And so if there were no friction, well, okay, I'm sorry, it's still kinetic friction, so it's sliding. And so the block is sliding, it's at rest relative to the ground, the block is. So the sled is sliding to the right, and in this case, the sled is the object. So the frictional force that the block exerts on the sled is in the opposite direction of the object, which is the sled, relative to the agent, which is the block. And so that points off to the left. All right. So if we, again, look at the positive x, positive y axes. Now, I'm just going to I'm going to look immediately at the x-axis first, because it looks like this has got my really what I want in it. And so here, if I say that the positive axis is off to the right, I can say that the magnitude of my tension force minus the magnitude of the frictional force of the block on the sled is equal to the mass of the sled times the acceleration of the sled. Well, the tension is twice the original force that's applying the tension on the string, and the force of friction of the block on the sled is equal to the force of friction of the sled on the block, which we found in the first part. So we can say that the force of the sled on the block is equal to the magnitude of the force of the block on the sled. So that is mu sub k mass of the block times g. and that's equal to the mass of the sled times the acceleration of the sled. Well, we also found that the force was equal to the tension in the string, which is equal to which is equal to the frictional force, and we did one too many steps, really. We have the magnitude of the tension is equal to the frictional force. So we have twice the frictional force minus the frictional force is equal to the mass of the sled times the acceleration of sled. So we just have the frictional force is equal to the mass of the sled times the acceleration of the sled, which is equal to mu sub k, coefficient of friction, mass of the block times g. So the acceleration of the sled is equal to the coefficient of kinetic friction times the mass of the block over the mass of the sled times g. So what was important about this? I really like the importance of the visualization, going back to the model to determine what direction the frictional forces are going, opposite the direction of the object relative to the agent. The fact that in this case the block was at rest and continues to be at rest relative to the ground. What does that mean for the sled sliding underneath it? As well as if you have, even though we only had one string, because it was in contact twice with our object around this pulley, the tension force was twice the tension force in the string. So a lot of good ideas in this problem, and kind of a fun one that's worth going over carefully.